Assalamualaikum warahmatullahi wabarakatuh and good day. So in this video, we'll continue with sampling distribution. Okay, chapter 5. So in previous video, you have a little bit a concept of sampling distribution. Okay, how is it? So in this video, sampling distribution related to the normal distribution. So if you remember, you've learned or you have used normal distribution so many times. Okay, by theorem 7.1. Let's say you have y1, y2, yn, a random sample of size n from normal distribution. Okay, so you can see that your y1 from normal, y2 from normal, yn from normal distribution with mean mu and variance sigma square. Okay, remember when you have normal distribution, you have two parameters. When you have binomial distribution, you have two parameters as well. If you have Poisson distribution, you have one parameter. So here, normal distribution, you have mean mu, variance sigma square. Then your y bar is the summation of yi divided by n is also normally distributed with mean mu y bar equal to mu and variance of y bar equal with sigma square over n. Okay, so this is the theorem. That means if you have y1, y2 until yn is a random sample, okay, n random sample, and this one from normal distribution with mean mu and variance sigma square, then your sample mean distribution, okay, this is your sampling distribution for y bar, is also follow normal distributed with mu y bar equal to mu and variance equal to sigma square divided by n. Okay, so you can prove this. Okay, so look this one proving. Okay, the proving is very important. So you have y1, y2, yn. Okay, this one come from normal distribution. Okay, with mean mu, variance sigma square. So we can write like this: yi, I from 1 until n are independent, okay, normally distributed variable. So basically, from normal distribution that you have learned in previous chapter, you have this one, EYI equal to mu. That means for y1 equal to mu, y2 equal to mu, and so on. And then your variance for yi equal with sigma square. So you can substitute that. So you have y bar equal to this one. So can you open the bracket for this one? This one is also similar with y1 over n plus y2 over n plus until yn over n. And this one, you can see that 1 over n is a constant. So it's a a1, y1, a2, y2, and an, yn. So you can see your a1 is what? 1 over n is a constant. And then your I is from until n because you have n random variable. Thus, y bar is a linear combination of y1, y2, yn. Okay, this one you learned in previous chapter. And then by using the theorem 6.3, okay, we can apply to conclude that y bar is also follow normal distribution function because, you look here. In order for you to find the expected y bar, it will be the expected of 1 over n y1 plus until 1 over n yn. So this one you know that expect 1 over n you can bring out, and this one actually E is y1. This one is equal with mu from theorem 6.3. This one. Alright, so that's why you can substitute with mu plus until 1 over n mu. So here, finally you will get mu because this one, how you get mu? This one actually you have how many mu? You have 1 over n because you plus, isn't it? So 1 over n times with how many mu you have? N mu. So you simplify, you get mu. Alright? And then for variance y bar, similar. You have a linear combination of this one. So you can bring this, you can write like this. Okay, similar with this one. And you know that because you have variance, the A become 1 over n square. Okay, a square. If you remember the previous theorem, okay, actually you must remember. Okay, and then here when you have v y1, you will get sigma square, which is from this theorem 6.3. Okay, so you substitute the value, and then again this one similar. You have 1 over n square. Okay, so this one because you have many sigma square, it will be n sigma square So you substitute or you simplify this one, you get sigma square over n, this one. All right. So it's proof that when you have y bar, okay, this y bar follow normal distribution as well with mean equal to mu and variance equal to sigma square n. So this is called sampling distribution for y bar. Okay, so that's why I said that's why you said that's why I said just now you have y1, y2, yn. This one follow normal distribution, and then you know that this normal distribution you have y bar, you have expected y equal to mu and variance y equal to sigma square. So by using the previous theorem, by using the linear combination, you can prove that this y bar also follow normal distribution with mean equal to mu and variance equal to sigma square over n. Alright? And then under condition theorem 7.1, okay, you know that y bar is follow normal distribution function with mean mu and with sigma square, with the variance is sigma square over n. So that's why your z it become like this. So before this, we have z equal to x minus mu over sigma, isn't it? All right. So now, since we have y bar, so this y bar, we can also have z, okay? But instead of x, we will have y bar because now it's y bar, sampling distribution, minus mu y bar over sigma square, sigma y bar. So when you substitute this value, okay, you will get y bar minus mu, sigma over square root n. Okay, so this one actually you can rearrange like this. But if you remember this one, you have used this one in applied statistic course. Okay, so again, this one has a standard normal distribution. And then we will illustrate the use of theorem 7.1 in the following example. Okay, in this example. So this is the application that you've learned in applied statistics. So I just go through a little bit. Okay, so a bottling machine can be regulated so that its discharge an average of mu ounce per bottle. It has been observed that the amount of fill dispensed by the machine is normally distributed with sigma 1.10. So you can see here, we have mu, we have sigma. So here you can see we have sigmas known. Okay, and then a sample of n equal to 9 bottle is randomly selected from the output of the machine on given day. All bottle with the same machine setting lah. Okay, and the ounce will be fill a measure for each. So the question asks you, find the probability that sample mean will be within 0.3 ounce of the true mean mu for the chosen machine setting. Alright, so they ask you to find the probability that the sample mean. So the sample mean will be mu y bar. Okay, so how is it? So you know that from this equation, you know that you have sample equal to 9. So you have y1, y2, y9. Okay, you have this sample, okay, ounce to fill the observed, okay. Then you know that y is a follow normal distribution function. So this one statement, all right. So suppose we'll have mean equal to mu and variance equal to 1. Okay, because mentioned here sigma is 1. So if you square, you still get 1. All right. So by theorem 7.1, that's mean from previous theorem, previous slide. Alright, so y bar also poses a normal sampling distribution. Okay, but you know that the mean is mu, the variance will be sigma square over n, which is when you substitute the value will be 1 over n. So the question asks to find the probability, okay, if you look here, to find the probability that the sample mean will be within 0.3 ounce. So within 0.3 ounce, that's mean less than 0.3. Okay, and greater than 0.3. That's mean you have this one. Okay, Chebychev, and this is something to do with Chebychev theorem as well. So you can see that y bar minus mu. Alright, so will be like this. So here actually this y bar minus mu is also, you have the standard deviation here. It sigma over square root n. Okay, so each will be have that one. So you know that because y bar minus mu y bar over sigma y bar will have this one, okay, from this one, okay, from this theorem, then has a standard normal, So then you can substitute the value here. Okay, and then using the stat table and formula, Z table. Okay, so if you look this one, where's the area? So you can see that the area will be the left and the area will be the right, which is negative 0.9 here and 0.9 here. Okay, so the Z is between these two values. All right, so this is based on the statistical table formula from textbook. Okay, but in our class, you will use for our stat table. All right. So if you look your stat table, it will be page 31 if I'm not mistaken. Okay, you can check page 31 stat table, and then you can see that your Z is 0.9. So if you look your Z is 0.9, it will be 0.1841. Okay, so here because the from your table the value given is at the right. So basically you can do this lah, 1 minus 2 times this one. So you will get this one. All right. So in applied statistics, you find the error, the rejection area, isn't it? But this one, we want to see the value is between 0.9 and 0.9. So it will be inside here. That's why you will have 1 minus 2 area of this, then you get in the middle. All right, so you get 0.6318. So look page 31, okay, stat table, page 31. Look the Z value. The Z value is 0.9. All right, so if you look Z value 0.9, it will be 0.1841. Okay, then based on this concept, you will have 1 minus 2 times this one will be 0.6318. So the probability is 0.6318. The sample mean, okay, the Y bar tu, the mu Y bar will be within 0.3 ounce. Okay, the true mean. So basically the concept to actually, you can see, isn't it? We have here, usually this is mu. So you have left and right rejection area or estimation error. But here we want to see within what area, what value, A and B. So this is what you get lah, 0.9. But what is the probability inside here is 0.6318. Okay, so this one is not is application, but it's quite theory lah. Okay, it's theory compared to applied statistic. All right, so never mind. Try do this. Make sure you know how to use the table. All right, try look, and then if you have question for this one, please let me know. Right, and I think I stop here. I will continue the next example in the next video. Thank you, class.